Okay, I got a little bit of a late start to this, so it's going to post late, but the first time I started doing this, I was accidentally supplying power to my tablet through my laptop, and everything ran out of power, so whoops. So I'm restarting, but luckily we only had one request for today, to do problem 2 in section 13.7, which is a divergence theorem problem, and I had already written it out right here. Before I jump into it, I do want to talk through like how we know this is a divergence theorem problem. I know you're told in web work, use the divergence theorem, but if you weren't told that, how would we know that that's an appropriate method to use here? So in the problem, we're being asked to evaluate a surface integral. And when we first learned surface integrals, we learned this kind of direct way to do them, where we dot f with the normal vector, and then convert sort of surface area to flat 2D area. And we can still do that for any surface integral problem we have, but divergence theorem is a way that we learned you can convert a surface integral, which is kind of complicated, to a triple integral, which can sometimes be a little bit easier. The rule for that being that our surface has to be closed, and luckily in this case our surface is closed. This notation on the double integral means it's closed. And also when I sketch out this shape, you'll see that it's closed. We also learned that you can evaluate surface integrals by like converting between surfaces using Stokes' theorem, but in that case you would need an open surface that you can describe like kind of connected two different ways by a boundary, so it wouldn't quite work in this case. So the shape that we're looking at is the closed hemispherical surface given by z equal this thing and the disk x squared plus y squared less than or equal to 1. So if you couldn't visualize that to start, it would have given you trouble with identifying this as a divergence theorem problem. But z equal to root 1 minus x squared minus y squared is this hemisphere. So just the top half of a sphere, because it's the positive square root, so that's the positive branch of this shape. It's got radius 1. I drew it a little lumpy, but it's supposed to be half of a sphere. And then, by itself, z equal root 1 minus x squared minus y squared would be an open surface. It's kind of like an upturned bowl. But we combine it with this x squared plus y squared less than or equal to 1, which is this shape down here. I don't know how to make that go away. Well, there. This shaded region down here. It's a circle with radius 1 in the xy plane. And so taken together, this whole thing is, I don't even know, like a bowl with a lid, I guess, sitting upside down on a table. And so since this surface is closed, we can use the divergence theorem on it. Importantly, we told that it's outward oriented, which is what the divergence theorem is written for, so we don't have to do any like sign swapping at the end. So we can go ahead and just apply divergence theorem, which is that this double surface integral over a closed surface is going to be the same as evaluating a triple integral of a scalar quantity, the divergence, over the volume inside the surface. So first up, we're going to need to know the divergence, and then we're going to have to set up a triple integral and evaluate it. So evaluating the divergence is sometimes easier than setting up bounds and stuff, so I recommend doing it first. That way, even if you can't finish the problem, you've got a chunk of it done. And that's going to be taking the derivative of the I hat component of f with respect to x plus the derivative of the j hat component with respect to y and the derivative of the k hat component with respect to z. So the derivative of 10x y squared z with respect to x is just 10y squared z. The derivative of 10y x squared z with respect to y is just 10x squared z, and the derivative of z squared with respect to z is 2z. And I'm going to go ahead and write that as that factored out quantity, just sort of pulling like terms out. If you don't do that, you'll be fine eventually, but keeping it in this simpler form is going to make some of the substitutions I want to do later a little bit easier. Whenever I see an x squared and a y squared, I try to write them together because I know that if I convert to polar coordinates, that x squared plus y squared is something easier to handle than x squared and y squared by themselves. So that's my thinking there. If those partial derivatives went a little bit quick for you, you know, it's been a while since we did them, so go ahead and slow down and make sure you understand, like treating y and z as a constant with respect to x and so on. But now that we know del dot f, we need to set up our triple integral. I'm going to give myself some space to write that out. And then del dot f is just going to go in there. And we learned 3 different ways to set up triple integrals, Cartesian, cylindrical, and spherical. And we get to pick whichever way we want to set it up. When I was working with people in class right before Thanksgiving break, we saw an example of like different people doing every single approach. And so if there's a particular way you want to do this, just go ahead and go for it. I'm going to do cylindrical because I like that one the most for this problem. You're thinking about a hemisphere, so spherical might make sense for the way you set up the coordinates, but I don't like that I don't see an x squared plus y squared plus z squared. That's the term that goes away in a nice way when you're doing spherical coordinates. I only see x squared plus y squared. So that's the thing that goes away in cylindrical coordinates. Cartesian I don't like because this square root of squares seems difficult to work with. But I'm pretty sure everyone who did the different methods got an answer eventually. So, since I decided I'm going to be doing cylindrical coordinates, I'm going to need, I have no idea why that thing shows up sometimes, it's fine, r dz dr d theta. And my z is the hardest one to set up, I think, so I'm going to start there. My lower bound for z is down here, and my upper bound is up there. So z is bounded below by 0. I don't go below the xy plane, so the smallest z ever is 0. And then it's bounded above everywhere by this hemisphere shape. So that would be root 1 minus x squared minus y squared. But in cylindrical coordinates, I can only have things depend on r, theta, or z. So I need to remember that x squared plus y squared is r squared. So instead, my upper bound is root 1 minus r squared. And then this x squared plus y squared that I had inside my integral actually has to be converted to r squared as well. I really wish that would stop. Sorry, everyone. Then to set my r and theta bounds, that's where we think about the shadow that our shape casts in the xy plane, or the widest point of it. How much r and how much theta do you need? And r is measured from the origin out to the edge of the surface. So the smallest r ever is a 0. We don't have a hole or anything around the origin. We do go down to the center of it, and r doesn't take on negative values. And then it goes out to radius 1 at its widest. The widest this bowl shape ever is at the xy plane, and there we're bounded by x squared plus y squared less than or equal to 1. So the upper bound for that is r squared equals 1 or r equals 1. And then theta, I think, is usually the easiest one for us. We have a full circle shape that goes all the way around, so my bounds are going to be from 0 to 2 pi. And then at this point I have bounds for all my variables, z, r, and theta, and inside my integral I only have z and r and theta, but theta just doesn't appear. So this is set up completely in cylindrical coordinates. I don't have any lingering x or y, so I can go ahead and evaluate this. So I guess that's what we're going to do. So my first integral is with respect to z, and I just have one z there. So I'm going to leave everything else the way it is. And then my 2z integrates to z squared, which is just evaluated from 0 to root 1 minus r squared. So I just integrated this thing. And when I plug in those bounds, I'm going to get, this is 0 to 2 pi, 0 to 1, 5r squared plus 1r times 1 minus r squared. Because root 1 minus r squared squared is just 1 minus r squared, and then the I would also have minus 0, but that just doesn't appear. And then I've still got my dr d theta left to take care of. What is going to be the best way to do this? I think I'm going to do a u sub. You could factor this out and evaluate it, and I think you would be fine. But then there's lots of high powers, and I don't want to deal with them. So yeah, I think that's the way I want to do it. I want to take u equal to r squared, then du is 2r dr, or r dr is du over 2. So I'm going to have 5u plus 1 times 1 minus u, and then this r dr becomes du over 2. And then I would have to change my upper and lower bounds, but 0 squared is 0, and 1 squared is 1, so I don't have anything to change here. So I'm going to pull that 1/2 out. I've got 0 to 2 pi, 0 to 1, 5u plus 1 times 1 minus u, I think. Let me just make sure I got that right. 5u plus 1, 1 minus u. Yep. Okay, now I'll go ahead and factor it. I'm going to have 5u minus 5u squared plus 1 minus u du d theta so that's minus 5u squared. I guess I don't need those parentheses. Minus 5u squared plus 4u plus 1 du d theta. And now I'm ready to integrate with respect to u. I'm actually going to do that here. I'm worried I'll run out of space. So I integrate u squared up to u cubed and divide by 3. I integrate u up to squared and divide by 2. and 1, a constant, becomes u to the power 1. And all that's going to be evaluated from 0 to 1, d theta. So I'm going to get negative 5/3 times 1 plus 4/2 times 1 plus 1 minus 0 minus 0 minus 0, which I'm not going to write that here. And that 4/2 is 2, I guess. So I've got minus 5/3 plus 3, but 3 I can write as 9/3. So that leaves me with 9 minus 5 is 4/3. And I can pull that constant out with my 1/2. So this becomes 4 over 2 times 3. Or just 2/3. And that last integral is the easiest. D theta just becomes theta, evaluated from 0 to 2 pi. So then when I plug in, I have, 2 pi minus 0, or 2 pi. So this is just 4 pi over 3.